Understand that a positional notation system could use any number of symbols as long as it uses at least two. So you could have a base 3 system, or a base 18 system, or a base 1017 system, or whatever. And so the decision to use base 10, that was really just an arbitrary historical decision. It was likely because we have 10 fingers and 10 toes, so it seemed natural to people to use base 10. And in fact, some civilizations like the ancient Babylonians used a base 12 system, because that fit best with their calendar. So let's look at the positional notation system, which uses something other than base 10. The base 8 system is called octal, and it uses just 8 symbols. Rather than contriving new symbols, we just use the same ones we use in decimal. We just use 8 of them rather than all 10. And so when you cycle digits in octal, when you get to 7, you go back to 0. And this is in fact the only difference between octal and decimal, is that you are using fewer symbols in octal. So let's see how this plays out. When you have the quantity 7 and you wish to express 1 higher, the 7 cycles back to 0, and then the digit to its left cycles to 1. So the quantity 1 higher than 0, 7 is 1, 0. And while it is very, very tempting to read this as the quantity 10, it is not. It is the same quantity which in decimal would be written 8. And this is really the hard thing about alternative number systems, is that it's very hard to look at a number and not immediately think of the quantity which it is in decimal. Because you're so used to decimal, it can be hard to accept alternative number systems. So let me illustrate octal a bit further. Here are some octal numbers on the left and their decimal equivalents. Notice down here that the quantity represented in octal as 20 is actually equivalent to the quantity represented in decimal as 16. The exact same rules are in effect, it's just that we're cycling from 7 to 0 rather than from 9 to 0. So here when we get to 7, express 1 higher, 7 cycles to 0, and the digit to its left, this 1, cycles by 1 to 2. Exact same principles, just different number of symbols. I think the thing which makes alternative number systems very hard for learners to accept is the fact that our natural language presumes decimal. So say in English, if you see 4 and 2, you immediately leap to 42. And 42 strongly implies 4 tens and 2, which is in fact correct in decimal, but if this were supposed to be octal, then the quantity it represents is actually 4 eighths and 2. That is decimal 34. So the problem is that the way we read it in English strongly implies the quantity which it doesn't in fact represent. And it's hard to mentally deal with this. So the solution is to always read non-decimal numbers digit by digit. So say, if this is meant to be octal, we would say 5637 octal. We just read each digit. And you should always say the base at the end so others know what you mean. If you just said 5637, they wouldn't necessarily know what base you mean. So we've looked at octal, which is a system that uses less than 10 symbols. Let's look at a system with more than 10 symbols, and base 16 is such a system, and it's called hexadecimal, or just hex for short. The story goes that IBM in the 1960s, when it came up with the term hexadecimal, they were just trying to avoid calling it sexadecimal, which is actually more proper. Hex is actually a Greek prefix, whereas decimal is derived from Latin. So to be consistent, it should have a Latin prefix, which is sex. But being a big American corporation in the 1960s, they couldn't call it sexadecimal. So hexadecimal uses 16 symbols, and being unimaginative, the IBM engineers just went with the Arabic numerals for the first 10, and then the first 6 letters of the alphabet for the rest. As a fun consequence of this, some hexadecimal numbers can look like words. So bad, beef, feed, dead, those are all examples that could be hexadecimal numbers, though they might look like words. And this is exactly the sort of thing that amuses programmers. And you should know that you'll see both lowercase and uppercase A through F in hexadecimal numbers. So to illustrate, here are the first hex numbers on the left and their decimal equivalents on the right. So you go from 1 all the way down to F, which is the equivalent of 15 in decimal, and then once you hit F, F then cycles to F goes to 0, and so the digit to its left goes to 1, so F goes to 1, 0. And then 1, 0, 1, 1, 1, 2, 1, 3, 1, 4, 1, 5, 1, 6, and so on until you get to 1, 9, 1, A, 1, B, 1, C, 1, D, 1, E, and so on. Understand that you get the same cascading effect in these alternate number systems as you do in decimal, whereas in decimal when we had a bunch of 9s on the rightmost digit places of a number, then you got this cascading effect when you expressed one higher. Well, F is the last symbol in hexadecimal, and so if you have a whole bunch of F's in the rightmost digit places of a number, you're going to get the same cascading effect. So 1 higher than 356 FFFFF is in fact 357000000. In daily life, we can just assume that any number we see is meant to be decimal. This is not the case in programming, however, so it would be very nice that if we had some sort of indicator that explicitly told us what base a number is supposed to be. Because say if you had 3261, this could be octal, it could be decimal, or it could be hexadecimal, and we couldn't tell just by looking at the digits. Of course, if it had, say, a D in it, then you would know, well, it can't be decimal, and it can't be octal, so therefore it's hex. But still, it's often nice to have an explicit indicator for those cases where it's ambiguous, such as in this case. However, there aren't really standard ways of indicating the base of a number, though there are some common conventions, and the most popular one that I know of is, say, to indicate an octal, you start it with a leading 0, and so because of this leading 0, this is meant to be interpreted as octal. I think this is a pretty lame system, but it's a common one. Hex is often indicated with 0x in front, so this is the hex quantity 3261. Another way of representing hex is to simply put an h at the end, so 32618 hex, either capital or lowercase h. And these aren't the only ways of indicating this number. It's really kind of a thing that's specific to, say, a particular programming language, like in one particular language they use one system. Though typically what happens is that decimal numbers, any number that doesn't have an indicator on it, a base indicator on it, is assumed to be decimal. So if you see 3261, you should assume that it's meant to be decimal.